Hi guys, Miss O'Connell here. So we're going to start with the analysis and just talking about a few pointers from the previous lab that we worked on, which is the cart on a ramp lab. And the objective in that lab was to model or picture the graphs for an object that has a constant acceleration. So we collected the three graphs, you printed those out, and hopefully you got through the first part of the analysis question where you're annotating the graph and identifying segments in its motion. So for the first part of the analysis, you are looking at the segment in which you push the cart with your hand. Where is the cart rolling freely up and down the incline? On the velocity versus time graph, you're denoting where the cart had reached its maximum velocity, which we said was technically in two places. And then on the position versus time graph, you're locating the highest point or the highest position of the cart on that ramp. So your position versus time graph is going to look something like this, hopefully a little bit clearer of a parabolic curve, but you should have denoted on your graph where the object is rolling up the incline. So we're starting from a position of 0, 0, as we had zeroed our sensor. As time increases, it's going to roll up the incline. So the cart is freely rolling up the incline. When we reach the maximum position, we are at the maximum in our parabolic curve. Okay, the slope at that instant is 0. So the slope of the graph at that position is 0. So we know that the velocity is 0 for an instant right before the object changes direction and begins rolling back down the ramp freely. We'll see on our velocity versus time graph at that exact instant where the object reaches the highest point on the incline, the velocity at that instant is 0. So our linear line is going to intersect the v is equal to 0 segment there at that exact time interval. So you can see at that exact time interval, your velocity versus time graph should cross the 0, 0 marker. You're giving your car a push. You know that it is slowing down at first. So you should see your velocity start at a maximum positive. That velocity is going to decrease until it reaches the maximum height on the ramp. And then as it begins to change direction, that velocity is going to become more and more negative as the cart speeds up as it rolls down the incline. Last but not least, I hope your acceleration graph looks a little bit better than this, but last but not least, we should see a constant horizontal line on our acceleration versus time graph. We know that if there's a constant force of gravity acting on the object, we're going to have a constant acceleration rate. That constant acceleration rate is going to be negative. Okay, this must be true in order for the object to be slowing down at first. If it's moving up, the velocity is positive. For it to slow down, the acceleration must be negative. On the way down the incline, the object's going to speed up. If the object is speeding up and the velocity is negative, acceleration must be negative. Okay, the signs for acceleration and velocity tell us whether the object is speeding up or slowing down. So if the object is speeding up and the velocity is negative, acceleration must be negative. So therefore, our acceleration is negative throughout the entire path of motion. So even at that time interval, when our object has reached its maximum height, at that maximum height, we have a 0 velocity, but our acceleration rate is still constant. Our acceleration is constant at that point. For the analysis question, specifically 2B, you want to estimate from your acceleration versus time graph what the acceleration rate is at that maximum height. Okay, basically by reading your graph, reading your tidal axes there. Okay, you want to do the same thing for 2A and B. You're going to physically read your graphs to come up with those responses. For part 2, this might require you to collaborate with those who used Logger Pro and collected the data. So for the second set of analysis questions, which are from 4, 5, and 6, you are going to need the equations of the lines from the graphs, and you'll also need the mean or average acceleration from the graph. So you might need to contact some group members to get those data points if you did not get there in our last class. For our first graph using Logger Pro, we analyzed and fit a curve fit. Specifically, we have a polynomial fit to the second order. So we have a times t squared plus b times t plus c. Okay, and t is obviously time, and x is position. So that gives us a position as a function of time equation. So we could plug in any value for time and we'd be able to predict exactly where on the ramp the cart will be located. So you should have that equation written out on your physical graph. So for example, my graph here is flipped. My direction is flipped. Your parabolic curve is going to be in the positive axis. But on top of my graph, I'm going to have my position function. So x is my position. Coefficient in front of time, I have 0.2, 88. So I'm going to round that to 0.29 times t squared. Plus b, but b is technically a negative value for me. So I'm going to have negative 1.13 times t plus c. My coefficient for c, I have 0.42. Okay, so that equation should be somewhere on that graph. So you have a parabolic curve. So my graph should be modeled as a function of t squared. Okay, technically, to get from position to the velocity, if we don't have a straight line, right? If we have a straight linear line, we could just take the slope. We don't have a straight linear line, so what we could do, actually, is we could take the derivative of that function, that position as a function of time function. We could take the derivative in respect to time to get the equation for velocity in respect to time. But technically on Logger Pro, we can use the software itself to find the equation for velocity. And to do that, we just fit a linear trend line to our data set. And that's going to give us the velocity as a function of time. If we plugged in for t, we could determine the speed of the cart at any time t. So my slope here, I have 0.59 t. And my y-intercept is actually negative here. Again, my graph's flipped. So my velocity as a function of time is going to be 0.59 t minus 1.2. I'll round up a little there. Okay, that's my velocity as a function of time. You'll notice here that it's giving you the slope of this line for you. And you'll notice the units on that slope, right? So the slope of a velocity versus time graph is our acceleration rate. And we can tell that by these units here. Okay, those of us who are in calculus also know that the derivative of this equation would give us the acceleration rate as well. But the slope of this linear line is going to give us acceleration. Okay, and we can tell by those units there. So that means that our acceleration, according to this linear trend line, the acceleration of our cart should be 0.59 meters per second squared. Your slopes should be negative because your direction is reversed. based on what you measured in lab. So your slopes are going to be a negative value. And in the analysis question, it refers to, in number 5, the graph of the velocity, okay? So by taking the slope of that velocity versus time graph. So underneath question number 5, you're referencing whatever your slope on your velocity versus time equation is. You're referencing that data point underneath analysis question 5. So our slope is 0.59 is our slope. That slope from the previous velocity versus time function and graph should resemble the acceleration rate that you can either read from your graph or analyze using Logger Pro. This is probably the portion that you didn't get to in class. So you'll need the person with the graphs to apply a statistical analysis to your physical graph. So hopefully your acceleration graph looks a little bit better than mine and is a linear line. But you can do this one of two ways. So you'll go to Analyze Statistics. It's going to give you the average value, the mean value from that linear trend line. Or you can do linear fit, and it'll tell you hopefully the slope is 0. And it'll also give you the acceleration value. The statistics function is a little bit easier to determine the information you'll need for 6. So I suggest that you highlight the segment of the graph that looks the most constant, head to statistics. It's going to give you the mean or average value for acceleration, which you might be able to read just from your graph. But we have 0.58 meters per second squared. Okay, and my previous velocity versus time graph, the slope of that line from the velocity versus time graph was actually 0.59 meters per second squared. So very, very close. Okay, in analysis question 6, it's asking you to compare the slope of your velocity versus time graph to the value that you can physically read on your acceleration versus time graph, or the mean average value. So just to clarify a little bit what these questions are asking you. So in question number 4, it's asking to analyze the acceleration versus time graph. Is the cart's acceleration constant during the free rolling segment? How do you know? Estimate the acceleration using the graph. So for that question 4, how do we know it's constant or if it's constant? Okay, so basically what evidence can you use from your graphs to support your response? So taking a look at your graph or even your graphs of motion, how can you tell that the acceleration of the cart is constant throughout the entire path of motion? And then you're just going to, the best you can, based on your graph, estimate what that constant acceleration rate is. In 5, it asks the graph of the velocity versus time graph is linear if the acceleration is constant. To fit a line to this data, it tells you what to do. You guys already did that in lab. You fit a linear trend line. It's asking you to compare how closely does the slope correspond to the acceleration you found in number 4. So in the previous part, you read the acceleration versus time graph. You looked at the acceleration versus time graph and you made an estimate. Looks like about, according to my graph, 0.5 meters per second per second. Okay, so you're comparing the slope to the estimate that you came up with. So my slope was 0.59. My estimate based on reading it was 0.5. So you're just going to comment on how closely those two numbers resembled one another. Mine had a 0.09 meter per second squared difference from what I could estimate on my graph and then what the slope of the velocity versus time graph actually was, according to the Logger Pro analysis. Last question 6. So it's asking or letting you know that the graph of acceleration versus time should appear approximately constant during the free rolling segment. How closely does the mean acceleration value compare to the values you found in 4 and 5? So in value 5, it was the slope. In value 4, that's what you estimated by reading the graph. So my value from 4, for example, is 0.5 meters per second squared. That's from reading the graph. From 5, that was the slope of the velocity versus time graph. That was 0.59 meters per second squared. And then last one, you're comparing it to the mean value, which you can find using the statistics function. Okay, so the average value of the acceleration, which is 0.58 meters per second squared. That's the average value on my acceleration versus time graph. So it's asking you to comment on how closely these three are related. In physics, we're talking about how closely something is related. We use percent difference. Okay, so in 6, the data or evidence we're going to need to produce is percent difference. So to calculate percent difference, your percent difference, you're going to take the difference between the two values and then divide by that average value. So for example, if I'm comparing my value from analysis question 5 to the mean acceleration, 5 is, again, is the slope of the velocity versus time graph. I'm going to take 0.58, subtract my mean average, which was 0.59, take the absolute value of that, and then divide by the average of those two. So I have 0.5 plus, 0.5, no. Okay, so we have 0.58 plus 0.59 divided by 2, and then times 100 to get our percent difference. So the difference between 0.58 and 0.59 is 0.01. I'm going to find the average. 0.58 plus 0.59, I get 1.17. Divide that by 2, I get 0.585. So I'm going to take 0.01 and divide it by 0.585, and then multiply by 100. So 0.017 times 100. I get that my percent difference is 1.7%. Your percent difference should be less than 10%. The values you find should be very, very similar. There should be a pretty small percent difference. Okay, and the reason being is because the equations themselves come from the derivative of the previous equation. So your slope and the actual acceleration value should be almost exactly the same. There'll be slight variations due to the fact that we're using a motion detector, which carries some error with it. Okay, so that's it for lab analysis. The lab sheet is due in our next class. Please correspond and work with your classmates if you're missing any information from the Logger Pro app. Send me any emails with questions.